good, like 25, 30 minutes, a lot of effort, you know. I think you'll find example 3 to be a little bit, somewhat less. So let's check it out. It says for r equals 2 sine of 3 theta. And by the way, let me stop right there. Without looking at your calculators, does anybody know what the shape of that graph is? It's a rose. Yeah, how many petals on this rose? That's right, Michelle, it's 3. And what size of a domain for theta would we need to trace the whole 3-petaled rose? 0 to pi, or just some distance of pi, right? That would get us there. Good. Okay, so anyways, it says find the rectangular equation for all tangent lines. So far, all the language probably seems relatively familiar to you. But then we look at this last little phrase here, the last 3 words, at the pole, might seem a little less familiar. So in polar lingo, what does the pole stand for? I mentioned it a couple of times, but it was in passing. So say again. It is the origin, yeah. So when you see the words at the pole, think origin.
How could there be more than one tangent?
You're about to find out. So maybe one thing we could do here, you really don't need to do this, but I think it'd be a good idea for us today. Let's go ahead and graph this rose, see what it looks like for real, and then we can kind of illustrate for Hayden why there might be more than one. Please be thankful that it's only 3 theta. If it was like 11 theta, there would be a lot more tangent lines for us to figure out. They wouldn't be that difficult to do, but there'd be more for sure. So take a minute and graph that. I will sketch it up here too, see what it all looks like. Kind of compare the graph with what we get. Let's see here. So does this look like that? The way I'm getting that is I'm plotting points. I'm plotting a couple of key points, trying to figure out which way it's pointed, knowing that it's 3-petaled and all that stuff. Kind of gives me some hints about what to do. Hayden, let me try to address your question first of how is it possible we could have more than one tangent line at the pole. So of course at the pole means the origin, and I'm off by a little bit on my drawing, like that whole cluster of where all the lines meet, that should be right at the origin, right? According to your graph. So I'll draw in a couple of tangent lines for you. I see one of them right there. And I see another one right there. And then my final one should be horizontal like that. So I'm seeing 3 tangent lines that are, of course, tangent to the curve and go through the origin or go through the pole. So we're going to end up with 3 linear equations. Let's talk about some really good stuff here, though. Finding the equation of a line. We're still talking about like y equals mx plus b or some variation, right? What is the best news of all as far as thinking about how easy it might be to finish this? Like, what do the words at the pole tell you about these tangent line equations? And so going through 0, 0, therefore, by extension, bless you, think about the linear equations, goes through 0, 0.
Y equals x.
Sorry?
Y equals x.
No.
Y equals blank x.
Right, okay, y equals mx.
Yeah, because it's 0, 0.
Keep going.
So their b is 0, so you don't have a b, so you don't have an intercept.
There you go. Well, it's not that you don't have an intercept. It's that your intercept is 0.
0.
That's the good news, right? Don't you normally have to take a little bit of effort to find the y-intercept, right? Here you won't. It's going to come down to, can you find the slope? I'll show you a little trick on how to do that. There's a very long way. There's a very short, tricky way. It's not even that tricky. You've already seen the formula. Just got to remember to do it, and it'll be over with pretty quick. Okay, so let's talk about what else is in play here as far as the principle. So you see a picture right there. See that, yeah, maybe there's going to be 3 tangent lines. Let's keep talking about at the pole / origin. But let's focus more about at the pole. Let's focus on that. So we're talking about a polar function, r equals 2 sine of 3 theta. I ask you to think a little bit more again here. So if we're talking about something happening at the pole, what does that mean about our polar function or our polar graph? If we're tracing these points as they form this rose, and we're talking about, okay, what's going on at the pole, what does that mean as far as the polar equation or graph? I've got a follow-up question, but I want to see if you can answer it just based on that. There it is, r equals 0, right? My follow-up was going to be, what does it mean about r if we're at the pole? So when it says at the pole, or at the origin, that means the radius is 0, right? Because don't all of our radial lines start at the origin and project out a certain distance, like a varying distance to form a rose or a limacon or a cardioid or whatever? Does that make sense? So one end is always at the origin or always at the pole. The other end is out there somewhere. So literally, if the point we're talking about is at the pole, that means we didn't move from the pole, meaning the radius is 0. So to get started with actually figuring out what these equations are, the first thing we're going to do is figure out the angles for which radius is 0, because that'll tell us we're at the pole. Okay, so let's try that. So 0 equals 2 sine of 3 theta. Again, here's where your trig skills and unit circle skills will pay off a little bit here. So 0 equals sine of 3 theta when we divide by 2. And what's your next step? Yeah, do the inverse sine or arc sine of both sides. So inverse sine of 0 equals 3 theta. For some of you this might be trivial, for others not so much. Inverse sine of 0. Where is sine 0? 0. And pi. Excuse me, 2 pi. Right? Okay, so let's see here. When I set that equal to 3 theta, let's see what happens here. So divide everything through by 3, we get 0, pi over 3, and 2 pi over 3 equals theta. Okay. And so does that seem, in your opinion at least, does that seem to go with the picture? When theta is 0, do you see that horizontal tangent line? Okay. And then pi over 3 would be the one that's kind of pointing into the first and third quadrants, and then the second and fourth quadrants would be the 2 pi over 3. Is that working okay? Okay. Any questions? Bless you. Okay, so then the final thing we want to talk about is how do we get this into a rectangular equation of a tangent line? So when we talk about that, we are talking about y equals mx plus b, or, of course, the point slope. Either one of them is going to be super easy for the reasons we talked about earlier. The fact that the y-intercept is 0, 0. It's going to make it much easier. So kind of the final big hurdle here is, does anyone remember the little relationship between theta and dy dx, right? Because dy dx will be the actual slope of the tangent line. That's what we want to have. But we have thetas. Like, how do we get from theta to dy dx? What does that involve? It's an old formula. We've used it. So that's a good conversion, and we could get there using that. That would be, I would consider that to be the long way. Like, we could go through like the x equals r cosine theta, y equals r sine theta, and develop the whole derivative thing. We could do that way. That would definitely work. But there's a faster way that I would encourage you to use. Hayden, you said something earlier? And that's kind of the same thing, right? We could go through and we could redevelop dy dx using, like you said, dy d theta over dx d theta, and plug in each of those points. But do you guys remember how huge dy d theta over dx d theta gets? Don't you have to use a product rule on the top and the bottom? No. Nope. Because math 8 of pi over 3 would just be 0, right? That's not really going to work. Or math 8 of, that's in terms of theta, it's just not going to work very well. There's a little formula. No, not recalling it. You're going to want to recall this. I'm glad we're going over this again. It's really important. Here it is. We looked at it, how did we look at it before? I think we looked at it like this. I think we said theta equals inverse tangent of dy dx. I think that's how we looked at it before. This is back in parametric. I think maybe I reintroduced it in polar, or in vectors. So, in order to make this work, we just need to do the tangent of both sides. So it'd be tangent of theta is equal to dy dx. That make sense? It's going to make this a million times easier than going through and redeveloping the derivative and then plugging in 3 separate points. This will make life much easier. Bless you. So, here we go. For the first one, what's tangent of 0? 0, yes. And so that means our first tangent line equation in rectangular form would be y equals 0x plus 0, right? Technically, y equals 0. And hopefully that goes beautifully with what you saw on the graph. Nice horizontal line right there on the x-axis. That's y equals 0, right? Okay. And then how about pi over 3? What is tangent of pi over 3? He asked it kind of like a question. What do you guys think? Is it really root 3? Yeah, it is root 3. You're totally right. You just didn't seem too sure of yourself, but you nailed it. Nice job. Positive root 3, right? So this would be y equals root 3 times x. Technically plus 0 again, right? Because we're at the pole, but we're not going to bother with that. And then finally, what is the tangent of 2 pi over 3? Negative root 3. Okay, so y equals negative root 3x. So there are those 3. That negative kind of got buried in there. Let's fix that. Let's just start over again. Y equals negative root 3x. There we go. Okay, and so you can see maybe that the root 3x would go with this one, and the negative root 3x would go with that one right there. So we have those 3 equations of the tangent lines at the pole. Grace?
How does it go from dy dx to y equals root 3x?
Sure. So we're using y equals mx plus b. So that's kind of the framework for our equation of the tangent line. We know from the fact that we're at the pole, we know that b is 0. Oops, that was way darker than I thought it was going to be. We know that b is going to be 0, and so that's, we're going to just say, hey, all the b's are 0, so they're not going to really show up. So the only thing we really have to know or have to figure out is m. And so the reason why we used all this stuff right here is because the only thing we had going for us is we had these 3 angles. So the question is, well, how do I go from an angle like, pi over 3 or 2 pi over 3 or 0 to a slope? And the way that you do that is the relationship between theta, tangent, and dy dx. What we really want, of course, is dy dx because that's the slope of the tangent line. And you know what? I could have put this maybe would have helped a little bit, equals m, right? Dy dx equals the m of the tangent line. And so then I'm just taking this y equals mx plus b and taking my m and putting it where it goes, recognizing that it's plus 0 in every case because we're at the origin for the y-intercept. That work? Okay, thanks for your question. Anybody else? Okay. Please, for your own mental well-being, please remember this relationship. Because if you got to go through and redevelop the polar derivative, dy dx, every time, it's going to be rough, right? For something like this, you'd have to do it 3 different evaluations. A lot of little details in there. Better to do it this way. Okay. If we're good, we're going to move on a little bit here for a couple of minutes. 0 would be this way. And then, of course, pi over 2 would get us all the way to pointing up. So this is actually going to give us a little too much. Because what this would do is this would sweep through this area. So it would catch this area in the first quadrant.
Please send Grace Seymour to the front desk with her car keys.
Wouldn't it catch that as well, though? Right? So that would be a little bit too much. That's not a bad idea. You're getting pretty close. Grace is on her way with her car keys. And like in 2 minutes, we're doing a fire drill. So Grace, I don't know how that's all going to work out, but okay. So Allie, that's a really good idea. But you've done a little too much. The idea of 0 looks like that's starting right on the edge of where a pedal begins. But instead of 0 to pi over 2, it should be 0 to something else. Pi over 3. Okay. So let's see what we think about that. So we're thinking pi over 3 would be like this right here. So that would go between those two. That would actually work, wouldn't it? Let's think that through. Don't the pedals start at the origin, at the pole? And so the way this would work is you'd say, well, when when theta is 0, r is 0, right? Because sine of 0 is 0 times 2 is 0. And when theta is pi over 3, it's a little more complicated. R would equal 2 sine of 3 times pi over 3. Bless you, that'd be sine of pi again times 0. So yeah, it'd be 0 again for a radius. So if we just change that to pi over 3, that would work. But that's not the only way. Will?
You just do 0 to pi and then divide that whole thing by 3.
Did you hear that? That's a great way to do it. It might not fit with every single multiple choice that you find, but if all you're doing is trying to find the area, I really like that. You just say, all right, let's go 1/2 times 0 to pi of f of theta squared, and that would give us the area within all 3 of them, right? So then if you just took that answer and divided by 3, that would give you the area within one of the petals of the flower, or the rose. That makes sense? So there's lots of different ways. We just touched on 2 of them. We could find lots of other ways. And so we'll continue to explore that as we go throughout these. Because if all you're doing is trying to find area, then there's really truly an infinite number of ways you could write that. But if you're doing like a multiple choice, and you're trying to match like a formatting, then you have to be a little bit better at like getting things to fit what you want. So this is just sort of the baby beginning. We'll do, I think, 4 or 5 examples. But I think we're about up to our time here. You guys are getting ready to go. So go to your purple class spot in the